In this lecture, we will continue our discussion of probability kernels and develop some new tools and new language for them. I should mention that what we are calling probability kernels are often called Markov kernels or Feller-Markov kernels, and the reason for that will become apparent in the next few lectures. Remember that a probability kernel over a pair of measurable spaces is a function from one space and the other sigma field into the unit interval that is a measurable function in the first variable and a probability measure in the second variable. Now, the first lemma that we proved about probability kernels is that we can integrate bounded measurable functions against them. In fact, we can take a function of both spaces and integrate it to get a measurable function out. In this lecture, we're going to focus on functions of one variable as input. So suppose that we have a bounded measurable function of the y probability space. We can then integrate it against q of x and dy to produce a function of x, which we know is measurable. The first observation I want to make is that it's also bounded. That just follows from the triangle inequality for integrals. Indeed, if I take that integral for each fixed x, its absolute value is therefore less than or equal to the integral of the absolute value of f of y, q of x dy. And f is a bounded function, which means that this integrand is less than or equal to the supremum of f, which means by the monotonicity property of integrals that this is less than or equal to the supremum over y of f of y times the integral of q of x dy. But that integral is constantly equal to 1 because q is a probability measure for each x. And so we see that for each x, this is bounded by the supremum of f, which is finite, and so this is also a bounded function of the first variable x in S1. Now, just a little bit of notation that we could have been using all along. For a bounded function of a measurable space, we can define its infinity norm to be the supremum. It's easy to verify that this is indeed a norm. The infinity comes from its relation to L infinity, which is the limit as p goes to infinity of LP. And in fact, this is a special case of a more general space. We can, if we have an additional measure on this measurable space, define the essentially bounded functions. And then this becomes their essential supremum. And that gives us a new Banach space in the realm of the LP spaces. For our purposes, it'll be fine to stick with genuinely bounded functions. We'll still call this norm the infinity norm for convenience. Now, also for notational convenience, let's give this new function of x a name. For any bounded measurable function of S2, let's define LQ of f to be this function here. LQF at x is equal to this. So what this calculation here actually shows is that this function, LQ, maps bounded measurable functions on S2b2 to bounded measurable functions on S1b1. And actually, what this shows is that the L infinity norm of LQF is less than or equal to the L infinity norm of f. This function LQ, defined between spaces of bounded functions, we call the Markov Generator associated with the probability kernel Q. I'd like to take a moment to develop some of the basic properties of this function LQ. First of all, it is a linear transformation from bounded functions of the y variable to bounded functions of the x variable. Now, that's just because it's defined by an integral, and so this follows from linearity of integration. Secondly, note that the constant function 1 is a function that is bounded on S2 and measurable, of course. And similarly, the constant function 1 on here is bounded and measurable. If we apply the Markov generator to the constant function 1 over here, we will get the constant function 1 over here. And that's simply because the probability kernel is a probability measure for each x. And that says that if I integrate 1, which is the definition of L1 of x, I just get 1. Now, this Markov generator is also positivity preserving. If I feed in a non-negative function of y, I get out a non-negative function of x. And that's just because q is a measure for each x. LQ of f at x is the integral of f at y, q of x and dy. So for each x, I'm integrating this non-negative function against this measure, which is therefore a non-negative number for each x. And the final basic property here is a continuity property. If fn is a sequence of bounded functions on S2, that are in the domain of the Markov generator, that is, that converge boundedly to a function f, then LQ of that sequence converges boundedly to LQ of the limit function f. That is, LQ is continuous under bounded convergence. Now remember that bounded convergence means that fn converges to f pointwise, and that each of the fn's is bounded by a constant m, which is fixed for all of the n's. In other words, in our new language, that's to say that the L infinity norm of f is uniformly bounded by some fixed constant m, say less than infinity. Well, as we showed on the last slide, the L infinity norm of LQ of fn is less than or equal to the L infinity norm of fn, which is less than or equal to m. And that shows that the sequence LQ of fn is also uniformly bounded. So we just need to demonstrate convergence. Well, if I take LQ of fn at x, that's the integral of fn of y, q of x dy. Now fn converges pointwise to f at y, and we have a uniform bound here for all of them, which as a function is an L1 function of this measure for each x. And therefore, by the dominated convergence theorem, the integral converges to the integral of f against q, which is LQ of f. So we get pointwise convergence of the function LQ of fn to LQ of f, and those functions LQ of fn are uniformly bounded, and so we do indeed have bounded convergence in the range as well. Now these seem like pretty basic properties, and the proofs of them were very elementary, but in fact those properties tell us a lot about the structure of the operator L. So in general, if we have a linear transformation L from bounded functions on one space to bounded functions on another space, if it's also positivity preserving, then it follows that it is monotone, in the sense that if f is less than or equal to g, where f and g are both real valued functions, then LF is less than or equal to LG, and they are both real valued functions by assumption here. That's just because if I take g minus f, by assumption that is a non-negative function, and that means that L of it is greater than or equal to L of 0, but L of 0 is 0 because L is linear. Well, since L is linear, that's also LG minus LF. And so that says that LF is less than or equal to LG. Now it follows from there that the absolute value of LF is less than or equal to L of the absolute value of F. That's just because both plus and minus F are less than or equal to the absolute value of F function, and therefore L of plus or minus f are both less than or equal to L of the absolute value of f by what we just showed here. But L is linear, and so that's plus or minus L of f. And if both L of f and minus L of f are less than or equal to this, then the absolute value of LF is less than or equal to that as well. Now, so far we've been focusing on real valued functions in these arguments, but in fact, we can allow our functions to be complex valued in all of these definitions with no problem. And this particular property here still holds for the complex modulus. If f is a complex valued, measurable bounded function on S2b2, then it still follows that L of f in modulus is pointwise less than or equal to L of the absolute value of f. The proof of that is very similar to our proof of the triangle inequality for integrals for complex valued functions. We start for each complex number, LF at x for fixed x, writing it as its polar decomposition, which will be the modulus of LF at x times e to the I theta for some theta that depends on x. That means that the absolute value of LF can be written as LF at x times e to the minus I theta. But L is linear, and indeed linear over complex linear combinations as well, since it's defined by an integral. And so that's equal to L of e to the minus I theta f at x. Now let's write this function in terms of its real and imaginary parts and use the linearity of L again. We can then write this as L of the real part plus I times L of the imaginary part. Now, for each fixed x, that tells us that this non-negative real number is equal to this complex number, which means that the imaginary part of this complex number must be 0. And so this is equal to this. Now, note that the thing inside L there, the real part of e to the minus I theta x f, is, as a real number for each x, less than or equal to the absolute value, or modulus, of that complex number that we're taking the real part of. But this phase doesn't affect that modulus, and so this is the same as the modulus of f at x. So that says that this real valued function is less than or equal to this positive function, and so by what we proved up here, we therefore have that L of this function, which is what we have equal to this, is less than or equal to L of the modulus of that function, which is exactly what we were trying to show. Now, all of that just came from properties 0 and 2 of the Markov generator, that it's a linear transformation here, and that it's positivity preserving. If we also throw in property 1, that it maps the constant function 1 to itself, then in fact we'll see that the L infinity contraction property, which we showed at the beginning, holds automatically just from those properties. Indeed, we know that f in here is bounded in modulus by its L infinity norm by definition, and that means by what we just showed that the modulus of LF at any point x is less than or equal to L of the modulus of f at x. The modulus of f is less than or equal to the L infinity norm of f, and that means, again by the monotonicity property here, that this is less than or equal to L of that. Now by linearity, this is the same as that constant times L of 1. And so if we know that L of 1 is 1, this is f L infinity norm. That's true for all x, and therefore taking the supremum here shows us that the L infinity norm of LF is less than or equal to the L infinity norm of f. Now it seems like we haven't really shown anything new here because we already knew that held for our Markov generator, but here L is not necessarily a Markov generator, it's just a linear transformation that satisfies properties 0, 1, and 2 from the previous slide. That's relevant because what we're now going to do is show that those properties 0, 1, 2, and 3 from the previous slide actually uniquely pin down that such an operator L is the Markov generator of a uniquely defined probability kernel, at least in the case where S1 and S2 are the same space, which is the special condition that we'll place from now on. So, suppose that we have a linear operator on the space of bounded measurable functions on S, and it satisfies those three properties that we proved do hold for a Markov generator. It fixes 1, it's positivity preserving, and it's continuous with respect to bounded convergence. Then it turns out there is a unique probability kernel that you can construct from it just like this. You apply that operator L to the indicator function of b, which is of course a bounded measurable function here. For each x, that gives you a new real number, and that function of x and b defines a probability kernel, again, on this pair, SB and SB itself. Moreover, if you now construct the Markov generator for that probability kernel, it's the original L that we started with. Let's see why this is true. First, as we showed on the last slide, If properties 1 and 2 hold here, then we have this more general monotonicity property. Now, the indicator function of b is a function that is pointwise in between 0 and 1. So it follows from there that L of 0, which is equal to 0, is less than or equal to L of the indicator of b, and that's less than or equal to L of 1, which by property 1 is 1. So that says that this function here that we're defining takes values in between 0 and 1. Moreover, if we take b to be the whole space S here, then of course we're going to get L of 1, the constant function 1, which is 1. So that means that to show that this defines for each x a probability measure, all we have to do is show that it's countably additive over countable disjoint unions of sets in B. So let's take a countable disjoint union. B is the union of some bk's. That's equivalent to saying that the indicator function of B is the sum of the indicator functions of the bk's. Now, if I take fn to be the partial sum of the first n of those terms, then we do have that fn converges pointwise to the indicator of b, and this convergence is bounded because all of the terms are less than or equal to 1 in absolute value. So therefore, by property 3, L of fn converges to L of the limit function. But that is our definition of Q on B for each point x in the domain. But by the linearity of the operator L, that is assumed in the definition here, this is the sum, k going from 1 up to n, of L of the indicator function of bk, and by the same vein, that is Q at the point x in question at bk inside the sum. So what we've shown is that the limit as n goes to infinity of the partial sum, k going from 1 up to n, of Q of bk is equal to Q of the point and b. And of course, this sum here is exactly the infinite sum that we're interested in. So that gives us countable additivity. So we have now shown that for each fixed x, Q of x dot is a probability measure on SB. That's half of what we need to show that it's a probability kernel. For the other half, if we take b fixed and consider this as a function of the first variable, well, that's just L of the indicator function of b, which by assumption is a bounded function measurable with respect to the sigma field b. And so this is, in fact, a measurable function of this variable by definition. And that's the other half of what we need to show. So Q is indeed a probability kernel on SB. Next, we need to show that the Markov generator of that probability kernel is our original operator L here. Well, from the definition of Markov generator, what that means is that we want to show that that operator L has the property that on any bounded function f, it yields the same value as LQ of f, which is just the integral of f against q. We want to show that's true for all bounded measurable functions f. Let's start by showing that it's true for indicator functions of measurable sets. If f is the indicator of b, then if I integrate the indicator of b against q, that's exactly q of the set b, but that is how we defined L of the indicator of b. And so that does show that for those functions f, L of f is the desired integral. So these two agree on indicator functions. By linearity of both sides, it follows that they agree on simple functions, and you can see how to go from there. In fact, this is yet another case where an application of Dynkin's multiplicative systems theorem will do the trick. So that shows that there is a bijection between probability kernels and Markov generators on a given space, SB. That is to say, if I start with a probability kernel on SB squared, I map that to the operator L, which is what we called the Markov generator, on bounded measurable functions where L of f is the integral of f against q. On the other hand, if I have a Markov generator L, which I now can define instead to be a linear operator on the bounded functions on SB, which satisfies properties 0 through 3 on the last few slides, I can map that to a probability kernel Q, which is defined by applying L to the indicator function of B. And so if I want to tell you, here's a probability kernel, I can equivalently tell you, here's a Markov generator, or vice versa. That's going to be very useful. One simple application right now will be showing us how to take products of probability kernels. See, if Q1 and Q2 are probability kernels over SB squared, then we can use this bijection to show that there exists a unique probability kernel with the property that its Markov generator is the composition of the Markov generators of the first two. In that order. Order matters here. In order to do so, all we have to check is that this is a Markov generator, which means we have to check that it satisfies properties 0 through 3. So is this composition a linear operator on the bounded measurable functions? Sure, you take two linear operators on a space and compose them, you get a linear operator on that space. Good. Does this composition preserve the constant function 1? Well, sure, because the composition just means you take LQ2 of 1 first and then apply LQ1, but LQ2 of 1 is 1, so this is LQ1 of 1, which is 1. Okay? Is it positivity preserving? Well, same idea. If f is a non-negative function, then if I take LQ2 of f, and call that g, by our assumption that LQ is a Markov generator, g is a non-negative function, and therefore the composition LQ1, LQ2 of f is just LQ1 of g. G is non-negative, and therefore this is non-negative, and we have the positivity preserving function. And same idea for property 3. If fn converges boundedly to f, then we know by assumption that LQ2 of fn converges boundedly to LQ2 of f. If I let gn denote LQ2 of fn and g denote LQ2 of f, then because we have bounded convergence of gn to g, it follows that LQ1 of gn converges to LQ1 of g boundedly. But LQ1 of gn is LQ1 of LQ2 of fn, and LQ1 of g is LQ1 of LQ2 of f. And so indeed we get bounded convergence of this to this. And that shows that the product LQ1 LQ2 is a Markov generator, which means that it is associated with a unique probability kernel, which we'll call Q. As we know, that probability kernel Q is defined by taking this Markov generator here and applying it to the indicator function of a measurable set. Now let's write down explicitly what that is, because it's going to be useful to us here. For the moment, if I write that inside function as g, this means by definition that I am integrating g of y against q1 of x and dy. But g inside here is just g of y is q2 of y and b. And so this becomes the integral of q2 of y and b against q1 of x and dy. More generally, if I want to integrate a function against this composition probability kernel, LQF at x, that's going to be the integral of q1 of x dy of the integral of q2 of y dz f at z. This looks an awful lot like doing product measure. And it would be doing product measure if these probability kernels actually didn't depend on those variables. Except that here we're only integrating it against a function of one of the variables in the product measure. Now we'll see in just a moment that we can just boost this to being a function of all the variables that are present here and give a generalization of product measure, which we will need later on. But for the moment, let's still consider this composition of LQ1 and LQ2. To understand this kind of product structure here a little bit better, let's look at the special case where the measurable spaces in question are discrete. Remember, we saw in that case, if S is a countable set and B is the full sigma field of all subsets of S, then a probability kernel is really a kernel function, And q of x and b you just get by summing that kernel function over all y in the set B. So in that case, if I try to integrate a function f against this composition of Markov generators, well, that's going to be a double sum over y and z from the previous slide of q1 of x and y, q2 of y and z, f at z. And it's elucidating to write this as the sum over z on the outside of the sum of y in S of q1 of xy, q2 of yz, all times f at z. That should look familiar. What we're doing here is matrix multiplication. In fact, that shouldn't come as a surprise because in this discrete context, just the action of a single Markov generator, LQ of f, is going to be a sum over y and S of q of xy, f at y. So this is again matrix multiplication of this matrix times this column vector. In other words here, what we're saying is that this kernel function q of xy is the matrix of the linear transformation LQ. It's the matrix in the basis of indicator functions of points x for x in S. So that representation requires us to use a particular basis, this natural one, whereas LQ is a more abstract basis-free linear transformation. Now, to conclude this lecture, let's again look at the case where we are composing a bunch of probability kernels or Markov generators in this way. We can actually integrate them against all of the variables present, not just a single variable. If Q1 through Qn are all probability kernels on a fixed measurable space twice, and if nu is a probability measure on that space, then we can take their product in this way. That is, there is a unique probability measure on n plus 1 copies of S, such that integrating a bounded measurable function against that measure can be achieved by doing this iterated integral here. We take the function of all n plus 1 variables that we'll call x0 through xn. We first integrate out the xn variable against the qn probability kernel, and that gives us a function of one fewer variable, but picking up some dependence of the n-1 variable from the probability kernel. Now that function is going to be a measurable function of all the variables in question, just from our basic lemma from 2 lectures ago about probability kernels. And by all the calculations we've just done, it's going to be a bounded function as well, which means that we can continue this operation and now integrate that function of x0 through xn minus 1 against the probability kernel qn minus 1 at xn minus 2 dxn minus 1. And continue down the line until you're integrating against the first one, which will give you a function of just x0 in the end, and then you integrate that against the fixed probability measure nu that you started with. This you should recognize as a generalization of the definition of integration against product measure that we did in the lectures on Tonelli and Fabini's theorem, and the arguments here to show that it's well defined and that this is true are almost exactly the same as the arguments there, so I'm not going to go through them in any detail. I'll just note that a good way to start is to take functions f that are tensor product functions. Now in that case, from this formula here, you can distribute this product throughout all the terms, and what you get is that this integral can be written as follows. Now this inside integral here in this special case is exactly the Markov generator LQn applied to Fn, and that's at the variable xn minus 1. And then you continue down the line, integrating now this as the input function for Qn minus 1, which means we'll be applying LQn minus 1 to that. And so when you're all said and done, what you'll see is that in this special case, this can be written as the following iterated integral operator. That is, we alternate between multiplying by a function and applying the Markov generator. Multiply by the next function and apply the Markov generator, and so on until you multiply by the final first function and then just integrate the whole thing against mu. Well, if you now apply this in the special case where the functions fk are indicator functions, this tells you how to define mu on product sets. And once you know how to define mu on product sets, Dinkin will get us the rest of the way to showing that there is a unique such measure and that this is a well-defined way to integrate against it. And if you're interested in working out the discrete case of what's going on here, you can write it out quickly. It doesn't exactly match up something that you've seen in a typical linear algebra class, because now this function of all the variables being used in that sum means that instead of matrix multiplication, we're involving higher order tensors. But we don't need to worry about that here. We will find integrals like this coming up a lot in the next lectures, because the next lectures have to do with Markov processes, which are one model of dynamical systems with random noise. And we'll see that probability kernels and their products like this tell us how we can understand the random evolution of those processes.